In this video, we discuss another example of greedy algorithms. We will discuss the minimum cost spanning tree, MCST, and Kruskal's algorithm and its C++ implementation. Billy will first explain to you what an MCST is.
We will discuss another problem that can be solved by a greedy algorithm. The problem is to obtain a minimum cost spanning tree, MCST, from an undirected graph. What is a spanning tree? A spanning tree is a subgraph of an undirected connected graph, which includes all the vertices of the graph with a minimum possible number of edges. It does not contain any cycle. A cycle is a path that starts from a vertex and ends at the same vertex. For example, in this graph, 0, 1, 7, 0 is a cycle. As an example, we can obtain a tree T from this graph by including these edges: 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 0, 7, 7, 8. This is the subgraph we thus obtained, and it is a tree as it does not have any cycle. As you can see, T has all the vertices, but only some edges of the original graph. This tree may not be minimum in the sense that the sum of all the weights, or costs, of its edges is not minimum. Here's our problem. Given an undirected connected weighted graph G, V, E, find a minimum cost spanning tree, or MCST, of G. We will discuss Kruskal's algorithm, which finds a minimum cost spanning tree. Using the greedy approach, the algorithm initially treats the graph as a forest, and every node it has as an individual tree. A tree connects to another tree only and only if it has the least cost among all available options. Let's consider this graph G to explain Kruskal's algorithm. Initially, each vertex of G forms a component, a single tree, and T is empty. We choose an edge with the least cost. If the edge joins the two vertices in different components, we add it to T. So, in this example, initially, we have components A, B, C, D, E, F, G. Since edge AD has a minimum weight of 5, we include it in T, and we merge the components A and D. Next, we choose the edge CE, as it has a minimum weight of 5 of the remaining edges. We include edge CE and T, and we merge the components C and E. Next, we choose the edge DF, which has a weight of 6, minimum of the remaining edges. We merge component AD with component F. Next, we choose the edge AB, which has a weight of 7. We merge the components ADF with the component B to form the component ABDF. Next, we choose the edge BE, which has a weight of 7. B is in component ABDF and E is in component CE. So we merge the component ABDF with the component CE to form the component ABCDEF. Next, we consider the edge BC, which has a weight of 8. We reject this edge because vertices B and C are in the same component ABCDEF. Next, we consider the edge EF, which has a weight of 8. We again reject this edge because vertices E and F are in the same component ABCDEF. Next, we choose the edge EG, which has a weight of 9. We merge the component ABCDEF with the component G to form the component ABCDEFG. Now we have one single component, or tree, A, B, C, D, E, F, G, so we are done. As you can see, this is basically a union find problem. We'll briefly review the union find problem later when we discuss the C, C++ implementation of this algorithm. Since a component always chooses a vertex from the outside, there won't be any cycle. Thus the final component is a tree. Since at each step, it always chooses the edge with a minimum weight, the total sum of the weights must be minimum. The tree thus obtained is a minimum cost spanning tree. The following shows Kruskal's algorithm. A graph G with a set of vertices V and a set of edges E is given. We use a set to represent the tree T, which is initially empty. We create a set for each vertex in V. We need to sort the edges, ordering them in increasing order. So each time we choose an edge, say, U, V, it always has the minimum weight among those which have not been chosen. The function find here returns the name of the component that the vertex is in. If the vertices U and V of the chosen edge are in different components, we include the edges UV in the tree T and we merge the two components where U and V are in. At the end, T is the MCST. Now let us see what's the complexity of Kruskal's algorithm. Suppose n is the number of vertices and m is the number of edges in the graph. The time to sort edges is of order m log m, which is equal to the order of m log n. This is because m is larger than or equal to n minus 1 but is less than or equal to n times n minus 1 over 2 as log n squared equals 2 times log n. In considering the time complexity of an algorithm, a constant does not matter. The time to initialize n disjoint set is theta n. The time for m union find operations is m times alpha n, where alpha n is a slow-growing function, slower than log n. The time for remaining operations is not more than n or big O n. So time complexity of the algorithm is theta m times log n. Next, we will discuss the C++ implementation of Kruskal's algorithm. As the algorithm requires set operations union and find, let's first briefly review the union find problem. In the union find problem, we have a group of disjoint sets. That is, the intersection of any two sets. Say A intersects B as an empty set. Suppose we have n elements, labeled as 1, 2, 3, blah 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 up to n. For example, we have 9 elements and they are in 3 disjoint sets. The first element in a set is the name of the set. Here set 1 has elements 1, 2, and 3. Set 4 has elements 4, 5, 6, and 7. Set 8 has elements 8 and 9. The operation find I returns the name of the set that I resides. For example, find 6 returns 4. Find 9 returns 8. The operation union A, B combines set A and set B to form a new set A. This can be done by representing each set A by an undirected tree dA. Union A, B is done by making root B a child of A as shown in these figures. After a union, we get a new set A which is the combination of the original A and B. These figures show union 1, 4, which gives a new set 1. After the merge, find 6 returns 4.
Now let's discuss the implementation of the algorithms. Okay. Now here's how we implement the union find. Okay. So we have to include these headers, okay, to set the algorithm. Yeah, we don't need the vector in this. Yeah. Now here's the union of two sets. Okay, set A and B, and so this is the merge set R. So we just use this function set union, which is in algorithm in this header. Okay, so in this format, Okay, we have from A begin to AN, from B begin to BN, and the result is in R. Okay, we need inserter. Okay, insert the result into R into the end at the end. Okay, and then we get the merge set. Okay, and we let A to be R. Okay, and then we make B to be empty. Okay, empty set again, and then we're done. So that's the union. Okay, and here's the find. We pass in the array of sets. Okay, and then A is the target. Okay, N is the number of elements in all the sets. Okay, so we just find from 0 to n minus 1. We start from 0 instead of 1. Okay, and then we use this function phi. Okay, again, this is algorithm from the beginning to end to find this A. If it is not there, that means we will reach the end of that set. Then we'll continue. Okay, otherwise that means we have found the target. Okay, so the set that the target is in, so we return I. Okay, if it is not there, we return -1. Okay, not in any set. Now here's an example of using the union find. Suppose our sets are labeled as 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we start from 0 instead of 1. Okay, so we create 10 sets of integers. Okay, and then from 0 to, or in this case, actually we label it from 1. Okay, starting from 1 because we have I plus 1 here. Okay, but we can start from 0 also. Okay, so we start from set 1. Okay, but the array is from 0. Okay, so we start from A plus I. Okay, to A plus I plus 1. Okay, so there's just one element in each set. So we have all these sets. Okay, so we print the sets out. Okay, for each of the sets, and then we union set 1 with 2. Okay, so 2 will go to 1, and then union 1 with 3. Okay, like what we do here, 1 and 4. Okay, so we come this set. 1 will be the root. Okay, so 4 now is in 1 in this example. So we merge these sets, and then here another example, we merge 4 with 5. Okay, and then 6 with 5. Okay, and then we print out the results. Okay, and then now here's the target. So 2, we know that after the merging, 2 should be in set 1. Okay, and then another example is the target 5. 5 should be in set 5. Okay, so we use this to find the target. Okay, so we compile this. Okay, and execute this. Okay, so you can see that we start from set 1. Okay, 0, 1, 2, 3, 4, 5, 6. Okay, so after merging this sets 1, 2, 3, 1, 2, 3. Okay, so we have this 1, 2, 3. That means 0, 1, 2 will be in this set 1. Okay, and 0 and 2 becomes empty. Okay, and then the other is 5, 4, 6. 5, 4, 6. Okay, so we get we get 5. We come have the elements 3, 4, 5. So in this case, 1 is in this set, okay. 5 is in this set, okay. I think I made a mistake here. It should be 3, 4, 5. Okay, the print out here is not right. Of 4, 5, 6 is right. It is 4, okay, and then 5, and then 6. 4, 5, 4, 5, 6, okay, or 5, 4, 6, okay, 5, 4, 6. So that contains the element 3, 4, 5, 3, 4, 5. Okay, so that's right, that's right. Okay. So there's the union find. Okay, and now let's go back to our Kruskal C++ implementation. Okay, now this is the algorithm. Okay, so we have to include this headers, okay, algorithm and set, okay, and list. Okay. And we use a adjacent list to represent the graph as we discussed before. Here we make some small modifications. So the adjacent list is like this. So a list represents the adjacent vertices of a vertex, okay, with the label of the adjacent vertex and the weights in it. Okay, so we discussed this before. So we define an edge class with a start vertex. Okay, start vertex means that the starting vertex, and end vertex, the ending vertex, and the weight of the vertex. Okay. And we define a function. Okay, so this is a little bit more complicated. So we define the function set is to set these variables, okay, to the values we want, okay, SEW. Okay. And we have to define the operator less than. Okay. This is to be used for insertion to a set, okay, given by the C++ library, okay, standard template library. Strictly speaking, this does not make sense because a set is just a collection of elements. It is not ordered. Okay. But I think they implement it this way to make the searching more efficient, because making the elements order, they can implement the set as a binary search tree, okay, a nearly balanced binary search tree, okay, and the search would be of the order log n rather than a linear search n. Okay. So we define the operator less than here. So if the weight, okay, the weight here is weight here is less than the weight on the right side, then we return true. Okay. So if they are equal, then we use this to distinguish between the two edges. Okay. If the vertex number is smaller than the right, then it is true also. Okay. Otherwise, we return false. Okay. Now here's the graph. Okay. So the graph class has data members and vertices, the number of vertices in the graph, and edges, the number of edges. Okay, and this is the list array to store the adjacency list. Okay. So we create a list of edges, okay, for that many lists. Okay, because NV is the total number of vertices. Okay, so we need to have that many lists okay, store the adjacent list. And then we construct the actually it works for undirected and directed, but here we consider undirected graph. Okay? So it is understood that if AB is an edge, BA is also an edge. Okay? So we construct that from the edges that we pass in. Okay? So basically we assign the data members to what we pass in for each edge. Okay? And then we put this edge, okay, into the corresponding adjacency list. Okay, we use the pushback function. Okay, put this edge in. Okay, so each list have these edges. So that's the constructor of this graph. Okay, and this is the display. We use an iterator to traverse all the adjacency lists. Okay, for each we do that from beginning to end, and then print out the vertex, okay, and the weight, okay, the vertex label, the starting vertex label and the ending vertex label, and the corresponding weight of the edge. Okay. We need to define another function called smaller weight. This is for sorting. Okay, sort again is a function defined in in algorithm here. So we make use of this sort, the C++ library, to sort the edges. Okay. So it is simple if this edge weight is smaller than this edge weight, okay, then it is true. Okay. Otherwise it's false. Now this is the union and find we just discussed. Okay. Now this is the Kruskal algorithm. Okay. Well, we have the graph passed in. So this is the strict implementation of this algorithm Billy just presented to you. Okay. So the set of the edge, okay, T, so that's the tree, the spanning tree that we want to get. Okay, and NV will be the number of vertices, NE the number of edges from the graph. Okay, and then we create a set for each vertex. Okay, so S and V. Okay, and then at the beginning, okay, we insert, okay, I into the corresponding set. Okay, so basically at the beginning, okay, each component, okay, is a set. Okay, so each component is a set. So each set contains the I, so we start from 0. We label the vertices from 0 to NV minus 1. Okay. And then we sort the edges. Okay. We sort the edges here. Okay, here. So we have that many edges. Okay. And the edges, and we use the iterator, okay, to extract the edges, okay, from the graph, from the graph list, so that we can sort them. So we traverse all the array, okay, the list array, okay, and then we obtain the edges by using the set function. Okay, so this iterator will point to an edge. Okay, so and okay, so that's the edge of where the iterator is pointing at. Okay, and then we set the array of edges, the k1 to the corresponding values. Okay, the starting vertex, ending vertex, the weight. Okay, and then we increment k. Okay, so we put all the edges in this array edges, and then we use this function to sort it. Okay, the C++ standard template library sort function. Okay, so we have to provide the pointer, the iterator, you can see that. Okay, address and all the way to the end, and then the compression is given by this function, smaller weight. Okay, that we discussed. Okay, smaller weight, so that we know we just sort according to the weight. Yeah. And then, so this part is basically what we discussed in this algorithm here. We now it is ordered. Right? The edges are ordered, so we just need to find whether U and V are in the same set. Okay, they're in the same component. Okay, if not, then we merge them. Okay, and also include the edge in the tree. Okay, so that's what we do here. Okay, so we iterate through the array. Okay, and here. Okay, we consider all the edges. Okay, and then we use the function find to find where it is. Okay, where the vertex, which component the vertex U is in. Okay, and this is to find which component, okay, that the vertex V is in. Okay, and if they are not in the same component or same set, okay, then we have to include that in our tree T. Okay, so we create this edge UVW. Okay, this edge UV. Okay, we include that in our tree. Okay, and also we have to merge this. Okay, union. Okay, to merge this. So we do that for all the edges. Okay, so that's the implementation of the algorithm. Now here's an example of testing using the example we discussed, except that here we label the vertices as 0, 1, 2, 3, 4, 5, 6 rather than A, B, C, D, E, F, G. Okay, so this is A to B 0 to 1 with weight 7, 0 to 3 with weight 5. Okay, it is this one. Okay, this graph. Okay, and now this is undirected graph. Okay, so it is a little bit sloppy here. We just specified once. So it is understood that if 0, 1 is there, the edge 1, 0 is also there. Okay, it is undirected. We are considering undirected, so we don't repeat it. Okay, so we just do it once. So there are totally 7 vertices. Okay, and this is to calculate the number of edges. Okay, so we use the constructor to construct a graph. The graph for the vertex set and the edge set. Okay, so we print out the original graph. Okay, so this is the display function. Okay, just to traverse the array to print out the vertex, starting vertex, end vertex, and the weight. Okay. And so we display that, and now we call this function. Okay, we have provided this graph. Okay, and this Kruskal function will return the set. Okay, and now you can print out all the address, but for us to be easier to read the address, we are going to create a graph for all the address of T. Okay, so we just again traverse T, okay, the set, okay, and put them into the array T address, okay, T address. We traverse it, put them, and then we create a graph. We call it MCST, okay, using this address, okay, with this number of address, okay, and number of vertices, okay, and then we print this out. Okay, now let's try this, compile this. Okay, we copy this. Okay. We compile. So that's what we have in this directory. We have just copied this, and then now let's paste. Okay, save it. So that's what we just copied. Okay, and then now we can compile this. So it compiles, and then we can execute. Okay, so you can see that this is the original graph. Okay, it is undirected, and this is the MCST. Okay, they obtain. Now, if you want to print it out using A, B, C, D, now you can easily do this in the display. So you can define this mapping character, maybe n equals a b b c d e F, G. Okay. And here we just print out the corresponding letter. So in this way, we can print out the characters. So you can see that this is the original graph. For this one, so AB is 7, AB is 7, AD is 5, okay. BC is 8, BD is 9, BE is 7, okay. CE is 5, and so on. Okay, and then the MCST. Okay, the MCST is this one. So you have AB, okay, 7, okay, the green lines, okay, and then AD 5, okay, BE 7, okay, CE okay, 5, okay, DF okay, 6, EG 9, EG 9. So so this corresponds to this MCST. So it works correctly. Okay. Now, if you don't want to modify the display function, alternatively, you could print out using character like this. Okay. So you define your address using A, B, C, D. Okay. Others are basically the same, and you change this to a character. So instead of int, you change this to character. Okay. And yeah, this you change that to character. Okay. Display is still the same. So basically, you need to change the int to character. Okay. Others remain the same. Okay. And then here, so in the algorithm, you have to minus if from the first offset A, capital A. Okay. So and others are the same. So if you do it the same this way, you could also obtain the printout using in characters, okay, in letters. Okay. Okay, so that's what we want to discuss today. Okay. Thank you for watching. If you think that the video is helpful to you, is useful, please click like. Okay. Bye.